Why do we need to know fracture mechanics? We need fracture mechanics for several reasons. Safety. Fracture mechanics helps us design safer and more reliable structures by predicting the conditions under which failure is likely to occur and developing strategies for preventing failures in the future. Through fracture analysis, by understanding how materials behave under different loading conditions, we can design structures that can resist failure and protect human life and property. Efficiency. Fracture mechanics helps us optimize the use of materials and minimize waste. By understanding the mechanics of crack propagation, we can design structures that use materials efficiently and avoid over-designing. Software tools like ABAX are invaluable for enhancing efficiency, as ABAX crack simulations offer an effective approach to comprehending crack propagation. Innovation. Fracture mechanics is a key driver of innovation in materials science and engineering. Through fracture analysis and by developing new materials with improved fracture resistance, we can create new opportunities for applications and advance the state of the art in many fields. Failure analysis. Fracture analysis helps us investigate the causes of failures in materials and structures and develop strategies for preventing failures in the future. By understanding the mechanics of crack propagation, as the context of ABAX crack, we can identify the root causes of failures and develop strategies for avoiding similar failures in the future. ABAX fracture simulation is a valuable tool in this process, aiding us along the way. You can see the Udemy course in the first comment. Now let's talk about the classification of the fracture mechanics. Fracture mechanics can be classified into two main categories based on the material behavior. Linear elastic fracture mechanics. The material is assumed to behave in a linearly elastic manner, which means that it deforms elastically under a small load and returns to its original shape when the load is removed. Linear elastic fracture mechanics assumes that the material near the crack tip behaves linearly elastic, meaning that the stress-strain relationship is linear and reversible. In linear elastic fracture mechanics, the stress intensity factor or the strain energy release rate at the crack tip is calculated to predict the critical stress or displacement required for crack initiation and growth. Fracture analysis using linear elastic fracture mechanics is typically used for analyzing brittle materials such as ceramics and glasses, where the material behavior can be accurately modeled using linear elastic assumptions. Elastic plastic fracture mechanics. The material is assumed to behave in an elastic plastic manner, which means that it deforms plastically under load and has a permanent deformation when the load is removed. Elastic plastic fracture mechanics assumes that the material near the crack tip behaves elastically plastically, meaning that the stress-strain relationship is non-linear and irreversible. In elastic plastic fracture mechanics, the J integral, or the crack tip opening displacement, is calculated using plastic zone size correction factors to predict the critical stress or displacement required for crack initiation and growth. Elastic plastic fracture mechanics is typically used for analyzing ductile materials, such as metals, where significant plastic deformation occurs. You can watch the complete course of fracture mechanics and fatigue concepts theory and ABAX software implementation on Udemy from the link in the description. Thank you for watching, subscribe for more, and see you next time.